thank you for visiting my YouTube channel. I know you want to watch the video. Before I get into the content, I'm going to talk about my nonprofit, the Accelerated Training Program, a cybersecurity and digital literacy nonprofit based in Charlotte, North Carolina. We are looking to provide accessible cybersecurity education and digital literacy skills to underrepresented groups from the K through 12 space right now, but we have on our roadmap collegiate, elderly populations, etc. Pretty much anyone from an underrepresented group. We want them to get cybersecurity education and digital literacy skills to bring them into the ever increasing digital world that we live in now. If that sounds like something that you're interested in, we do have a donate button if you would like to donate monetarily. We're always accepting donations. If you would like to volunteer your time, we have a volunteer tab where we're looking for workshop volunteers. Currently, we have 1 month workshops, but we're looking to expand that in 2024. Board members, advisory board members, and a grant writer. So if you're a grant writer, if you have experience in grant writing and also winning grants, we would definitely love to have you on our team. To be considered, please complete the volunteer form here, which is a link that will navigate you to a Google form. And again, we're a cybersecurity, digital literacy nonprofit, and we would love to work with you if that is your passion as well. Thank you. Have a good day. And now the video is going to start. Hello, and welcome to another Advent of Cyber video. As I said previously, I'm doing these rooms out of order. So today we're looking at day 14, machine learning, the little machine that wanted to learn. So let me start the machine. Okay, it's starting in split mode. Okay, so let's read. Okay. The CTO has made our toy pipeline go wrong. By infecting elves at key positions in the toy making process, he has poisoned the pipeline and caused the elves to make defective toys. McSkitty has started to combat the problem by placing control elves in the pipeline. These elves take measurements of the toys to try and narrow down the exact location of problematic elves in the pipeline by comparing the measurements of defective and perfect toys. However, this is an incredibly tedious and lengthy process, so he's looking to use machine learning to optimize it. So the learning objectives. What is machine learning? Basic machine learning structures and algorithms using neural networks to predict defective toys. Okay, so we just need the VM and it's going to be in split screen. Okay, so we've started the machine, so let's go. Introduction. Over the past decade, there has been a massive boom in artificial intelligence and machine learning systems. Just in the last couple of years, the release of ChatGPT has taken the world by storm. However, how these systems actually work is often shrouded in mystery, leading to a lot of snake oil sales tactics. In this task, we will provide you with a glimpse into the world of machine learning to help demystify this incredibly interesting topic. We will create our very own neural network that can be used to detect defective toys. So, zero to hero on artificial intelligence. Before we can create our own AI, we need to learn some of the basics. First of all, let's discuss the two terms. The term AI is used in broad strokes out there in the world, often incorrectly. We have to be honest with ourselves. AI can't just be a bunch of if statements. A better term to use is machine learning. Machine learning refers to the process used to create a system that can mimic the behavior we see in real life. This is because there is intelligence in real life in its structures. The field is incredibly broad, but here are a couple of popular examples. So, let's see if we can answer some questions. Okay, so is this machine learning? Yes. What ML structure aims to mimic the process of natural selection? Okay. Learning styles. First on our list of Machine learning basics is to cover is the neural network's learning style. In order to train our neural network, we need to decide how we'll teach it. While there are many different styles and subsets of styles, we will only focus on the two main styles for now. Oh, did I skip a paragraph? Oh, okay. So I think I skipped. My bad. Okay, so the field is incredibly broad, but here are a couple popular examples. Genetic algorithm. This machine learning structure aims to mimic the process of natural selection and evolution by using rounds of offspring and mutations based on the criteria provided. The structure aims to create the strongest children through survival of the fittest. So it's the genetic algorithm. Okay. Algorithm. Okay. What is the name of the learning style that makes use of label data to train the machine learning? Okay, so let's keep going. So we're looking for label. Okay, let's go. Okay. Particle swarm. This machine learning structure aims to mimic the process of how birds flock and group together at specific points. By creating a swarm of particles, the structure aims to move all the particles to the optimal answers grouping point. And then neural networks. This machine structure is by far the most popular and aims to mimic the process of how neurons work in the brain. These neurons receive various inputs that are then transformed before being sent to the next neuron. These neurons can then be trained to perform the correct transformations to provide the correct final answer. There are many more machine learning structures, but we'll stick to neural networks for this task, as they are the most popular. And while there's a significant amount of math involved in implementing a machine learning structure, we'll be abstracting this information. If you want to learn more, you can start here. This is where the room person started, and then work your way up. So, learning styles. First on our list of machine learning basics to cover is the neural network's learning style. In order to train our neural network, we need to decide how we'll teach it. While there are many different styles and subsets of styles, we will only focus on the two main styles for now: supervised learning. And this learning style will guide the neural network to the answers we want it to provide. We'll ask the neural network to give us an answer and then provide it with feedback on how close it was to the correct answer. In this way, we are supervising the neural network as it learns. However, to use this learning style, we need a data set where we know the correct answers. This is called a label data set, as we have a label for what the correct answer should be given the input. So it's supervised learning. Okay. What is the name of the layer between the input and output layers of a neural network? Okay. Let's go. Okay. Unsupervised learning. In this learning style, we take a bit more of a hands off approach and let the neural network do its own thing. While this sounds very strange, the main goal is to have the neural network identify interesting things. Humans are quite good at most classification tasks. For example, simply looking at an image and being able to tell what color it is. But if someone were to ask you, what is it, that color, you would have a hard time explaining the reason. Humans can see up to 3 dimensions, whereas neural networks have the ability to work in far greater dimensions to see patterns. Unsupervised learning is often used to allow neural networks to learn interesting features that humans cannot comprehend that can be used for classification. A very popular example of this is the restricted Boltzmann machine. Here, have a look here at the weird features the neural network learned to classify different digits. For this task, we will focus on supervised learning. It's an easier learning style for learning the basics, including the basic network structure. Basic structure. Next on our list of machine learning basics to learn is the basic structure of a neural network. Sticking to the very basics of machine learning, a neural network consists of various different nodes, neurons that are connected as shown in the animation below. So we have height, width, length, color scheme, maker ELF-ID, and checker ELF-ID. So these are the inputs. So this is the hidden logic that's being done, and then it determines if it's defective. As shown in the animation, the neural network has three main layers. Input layer, this is the first layer of nodes in the neural network. These nodes each receive a single data input that is then passed on to the hidden layer. This means that the number of nodes in this layer always matches the network's number of inputs or data parameters. For example, if our network takes the toy length, width, and height, there will be three nodes in the input layer. Output layer. This is the last layer of nodes in the neural network. These nodes send the output from the network once it has been received from the hidden layer. Therefore, the number of nodes in this layer will always be the same as the network's number of outputs. For example, if our network outputs whether or not the toy is defective, we will have one node in the outer layer for either defective or not defective. We could also do it with two nodes, but we won't get into that here. And so then we have a hidden layer. This is the layer of nodes between the neural network's input and output layers. With a simple neural network, this will only be one layer of nodes. However, for additional learning opportunities, we could add more layers to create a deep neural network. This layer is where the neural network's main action takes place. That's why I called it the logic. Each node within the neural network's hidden layer receives multiple inputs from the nodes in the previous layer and will then transmit their answers to multiple nodes in the next layer. Now that we understand the basic layout of neural networks, let's zoom in on one of the nodes in the hidden layer to see what it's actually doing. Okay, so it is the hidden layer. Hidden layer. Okay, what is the name of the process used to provide feedback to the neural network on how close its prediction was? Okay, so we see the input, we see the weights, input, weights, multiplied, you get a weighted answer, and then it's total value, and then you can tell if it's defective or not. Okay, as mentioned before, we will simplify the math quite a bit here. In essence, the node is receiving inputs from nodes in the previous layer, adding them together and then sending the output on to the next layer of nodes. There is, however, a little bit more detail in this step that's important to note. Inputs are not directly added. Instead, they are multiplied by a weight value first. This helps the neural network decide which input should contribute more to the output than others, and the addition's output is not directly transmitted out. Instead, the output is first entered into what is called an activation function. In essence, this decides if the neuron or node will be active or not. It does this by ensuring that the output, no matter the input, will always be a decimal between 0 and 1 or between -1 and 1. Now that we understand the neural network structure and how the layers and nodes within it work, let's dive into how the network is trained. There are two steps to training the network: the feed forward step and the back propagation step. So, what is the feed forward? The feed forward loop is how we send data through the network and get an answer on the other side. Once our network has been trained, this is the only step we perform. At this point, we stop training and simply want an answer from the network. To complete one round of the feed forward step, we have to perform the following. So we have a normalization of average of what the different nodes should be. We pass that as input, and then we pass it to the hidden layer, which does the logic, and then we get an answer. And so we see it is defective. Okay. Normalize all of the inputs. To allow our neural network to decide which inputs are most important in helping it to decide the answer, we need to normalize them. As mentioned before, each node in the network tries to keep its answer between 0 and 1. If we have one output with a range of 0 to 50 and another with a range of 0 to 2, our network won't be able to properly consume the input. Therefore, we normalize the inputs first by adjusting them so that their ranges are all the same. In our example here, we will take the inputs with a 0 to 50 range and divide all of them by 25 to change their ranges to 0 to 2. Feed the inputs to our nodes in the input layer. Once normalized, we can provide one data entry for each input node in our network. So propagate the data through the network. At each node, we add all the inputs and run them through the activation function to get the node's output. This output then becomes the input for the next layer of nodes. We repeat this process until we get to our network's output layer. Okay, so read the output from the network. At the output layer of the network, we receive the output from our nodes. The answer will be a decimal between 0 and 1, but for decision making, we'll round it to get a binary answer from each output node. So back propagation. When we train our network, the feed forward loop is only half of the process. Once we receive the answers from our network, we need to tell it how close it was to the correct answer. This is the back propagation step. Here we perform the following steps. So back propagation. So back propagation. Spell that right. Yep. Okay, so what is the value of the flag once we receive 90% accuracy? Okay, so let's keep going. So we are here. So we do the following steps. So we have our, it does, answer should not be defective. So input is 0.51, it's updated, so that means it needs to be 0.58. 0.48, excuse me, because you're going back. So it's like I have an output of 0.51, but I need to make it to where it's not defective, so it needs to be below 0.5. Calculate the difference in received outputs versus expected outputs. As mentioned before, the activation function will provide a decimal answer between 0 and 1. Since we know that the answer has to be either 0 or 1, we can calculate the difference in the answer. This difference tells us how close the neural network was to the correct answer. Oh, so it looks like we're doing the subtraction of, of 1. So here, 1 minus 0.49 is 0.48, 0.51. So that means the difference is 0.48. Okay, so update the weights of the nodes. Using the difference calculated in the previous step, we can start to update the weights of each input to the nodes in the output layer. We won't dive too deep into this in this update process, as it often involves a bit of complex math to decide what updates should be made. Propagate the difference between back to the other layers. This is where the term back propagation comes from. Once the weights of the nodes in the output layer have been updated, we can calculate what the difference will be for the previous nodes. Once again, this difference is then used to update the weights of the nodes in that layer before being propagated back even more. We continue this process of back propagation until the weights for the input layer have been updated. Once all the weights have been updated, we can run another sample of data through our network. We repeat this process with all our samples in order to train our network. Okay. Data set splits. The last topic to cover before we can build our network is data set splits. Let's use an analogy to explain it. Let's say your teacher constantly tells you that 1 plus 1 equals 2 and 2 plus 2 equals 4. But in the exam, your teacher asks you to calculate 3 plus 3. The question here is, have you just learned what the answer is, or did you learn the fundamental principle required to get the answer? In short, you can overtrain yourself by learning the answers instead of learning the required principle itself. The same thing can happen with neural networks. Overtraining is a big problem with neural networks. We are training them with data where we know the answers. So it's possible for the network to simply learn the answers, not how to calculate the answer. To combat this, we need to validate that our neural network is learning the process and not the answers. This validation also tells us when we need to stop our learning process. To to perform this validation, we have to split our data set into the three data sets below. Training data, this is our largest data set. We use it to train the network. Usually this is about 70 to 80% of the original data set. Validation data, this data is used to validate the network's training. After each training round, we send this data through our network to determine its performance. If the performance starts to decline, we know where we are starting to overtrain and should stop the process. Usually this is about 10 to 15% of the original data set. Testing data. This data set is used to calculate the final step of the network. The network won't see this data at all until we are done with the training process. Once training is complete, we send through the test data set to determine the performance of our network. Usually this is about 10 to 15% of the original data set. Now you know how a basic neural network works, so let's build our own. Okay, so we're about to put it all together. Now that we've covered the basics, we are ready to build our own neural network. Start the machine in the top right corner. Okay, you can find the files that you will be working on the desktop in the neural networks folder. You will be provided with the following folders: detector.py. This is the script where we will build our neural network. Some of the sections have already been completed for us. Dataset train.csv. This is our training data set. In this data set, the elves have not only captured the measurements of the toys for you, but also whether the toy was defective or not. We will use this data set to train, validate, and test our neural network model. And data east test. This is your testing data set. In this data set, the elves have only captured the measurements of the toys. Due to the sheer volume of the toy pipeline, they were unable to determine if the toy was defective or not. Once we have trained our neural network, we will predict which of the entries in the files are defective toys for McSkitty to remove from the pipeline. Our first step is to complete the detector.py script. Let's work through the initial code. It has already been added for you in the script as shown below. So let's open. Okay. So we see this here. These are the imports that we need for our neural network. NumPy is a powerful array and matrix library used to format our data. Pandas is a data processing library that also allows for reading and format data structures. This will be used to split our data. This will be used to normalize. This will be used to encode our text. And this will be used for the multi-layer perception. These are the color labels that we will convert to numbers. And then, so what we're doing is we're opening the training data set and getting the head. And then we're opening the testing data set and we're going to the head, which I'm assuming is to the top of the file. The neural network cannot take strings as input as we learned, so we need to encode the strings as integers. So this is where we're doing the encoder. We're fitting the data and we're getting the color scheme. So the color scheme is from the training data. We're getting the color scheme column. So training data color scheme. And so what we're doing is we're encoding that. And then we're doing the same again for the testing. And so now what we're doing is reading our training data from the CSV file, and then we're going to read the data that we're training. So training data, so this is what we're doing, and we're going to read the label of our training data. And then we're going to test. Okay, so let's work through what the code does. The first few lines are all the library imports that we need for our neural network. We will make use of pandas to read our data sets and scikit-learn for building our neural network. Next, we load the data sets. In our case, there is a training and testing data set, while we have the labels for the training data set, we don't have them for the testing data set. So while we can perform supervised learning, we will only know our neural network's true performance once we have uploaded our predictions for review. Once the data is loaded, we need to make sure that all the inputs are numerical values. One of our data types is the toy's color scheme. In order to provide this data to our network, we will encode the data. Variable X is used to store our training data set together with this label stored in variable Y. So lastly, test X stores the testing data set that we will use to perform the predictions on. So now we'll start adding code required to build and train our neural networks. Okay, so creating the data set. First, we need to create the data set. In our case, we will use the 80-20 split. So 80 is going to be used for the training, and then 20% is going to be used for testing. Okay, so we will combine our validation and testing data sets, as we will use the completely new data for our testing data set. To do this, we have to add the following line in our code. So okay, so copy this and paste. Okay. Now, this will split our training data set into two. Xtrain contains the training data, and Xvalidate our validation data. Ytrain contains the labels for our training data, and Yvalidate our labels for validation data. Okay, normalizing the data. Next, we need to normalize our data. We can do this by adding the following line in our code after the insert normalization code here. Okay, sample of our data. Okay, so I'm gonna copy, we'll paste. Okay. Okay, as you can see from the lines of code, we cannot cheat by determining the normalization on either the validation or test data sets. The normalization vector is only created from the train data, which is then applied to all three data sets. Okay, training the neural network. Finally, we can train our neural network. First, we will create our classifier with the following code after the insert classifier line. Okay, so we're gonna copy. Oh, hold on. So I want to go right there. Okay. You can find more information on this specific classifier here. Here's a bit of an explanation of what the values are doing. Solver. This is the algorithm used to update the weights. This is a classic back propagation algorithm, but others can be used as well. Alpha. The alpha value is used for the regularization of the neural network. We won't dive too deep into the math here, but we have selected a fairly default value. Hidden layer sizes. This tells us the structure of the hidden layers in our neural network based on the provided configuration. We have 2 hidden layers with 15 nodes each. Max iteration. This sets a cap on the number of iterations we can train our neural network before it is forcibly stopped. So we have set that to 10,000. Next, we can train our classifier with the following code. So this is where we train. Okay. When this step is complete, we have successfully trained our neural network. Okay, so now we're about to validate. The next step is to validate our neural network. To do this, we can ask the network to predict the values based on the validation data set with the following code. As you will see when you execute the script, predictions are significantly faster than training the network. This is why neural networks can actually be used in real life applications, as the prediction rate is incredibly fast once the network has been trained. We can determine the accuracy of our classifier by comparing the two arrays with the following code. So we have account correct, account incorrect. So while x is in the range of the length of y predicted, we do a check to see if y predicted equals validate y. And so if those equal, which means the prediction actually equal to what was validated, then it was correct. Otherwise, it's not correct and you're incrementing by one. Then you're printing, training has been completing, validating neural network now, and then you're printing out the correct and incorrect number of times. And then the accuracy is the count correct times 1 divided by the count correct and the count incorrect multiplied by 1. And that's the division. And then the network accuracy is the accuracy times 100, because this is a decimal value, and then adding the percent sign. As you can see, when we run this code, the neural network is pretty accurate. Okay, saving the poison toy pipeline. Finally, as a last step, we can now ask our neural network to make predictions on the testing data that was not labeled by the elves with the following code after the line. So okay, that is it. We are finally ready to train and run our network. Okay, so let me save. So now what I'm going to do is from a terminal, so ls cd desktop ls, oh, Python 3 detector.py. Okay. These predictions will be saved to a file. Upload your predictions here to see how well your neural network performed. If your accuracy is above 90, you will be awarded the flag, and McSkitty's toy pipeline will be saved. Okay. Neural network accuracy. If your neural network is not able to reach 90% accuracy, run the script again to retain the network and submit the new predictions. Usually within 2 training rounds, you will be able to reach 90% on the testing data. This does, however, raise the question of why the neural network's accuracy fluctuates. The reason for the fluctuation is that neural networks have randomness built into them. The weights for each of the inputs to the nodes are randomized at the start, meaning that 2 neural networks are never exactly the same, similar to how different brains might learn the same data differently. To truly determine the accuracy of your neural network, you would have to train it several times and calculate the average accuracy across all networks. Several other factors might also influence the accuracy of the network. For example, the quality of the data set. In machine language, there's a term called GIGO, garbage in, garbage out. This term is meant to illustrate that AI isn't this magical thing that can fix every single problem. A machine learning structure is only as good as the quality of the data used to train it. Without good data, we wouldn't be able to receive any accurate output. Okay, it's still going. Okay. So we have 91.73. So how was it saved? Okay, so the file is called predictions. And then let's open. Okay, we're going to open Firefox. Okay, cybersecurity applications for machine learning. Machine learning, or AI, as it is often called out there in the world, has real life applications for cybersecurity. Here are just some of them. As shown in the example today, machine learning structures are incredible at finding complex patterns in data and performing predictions on large data sets with incredible accuracy. While humans can often do the same, the sheer amount of data and predictions required can be overwhelming. Furthermore, the intricate connections between different inputs cannot often be determined by a human, whereas machine language structures can learn these decision boundaries in hyperspace, allowing for features to be connected in more than 3 dimensions. This can be used for classifications that are complex, such as whether network traffic is malicious or not. So, machine language structures are incredibly good at anomaly detection. If you provide a well trained machine learning structure with thousands of data points, it will be able to discern the outliers for you. This can be used in security to determine anomalies such as unauthorized account logins. As that's the phone. As machine learning structures have the ability to learn complex patterns, they can be used for authentication applications such as biometric authentication. Machine learning structures can be used to predict whether a person's fingerprint or iris matches the template that has been stored to provide access to buildings or devices. So, cybersecurity cautions for machine language. While there are many benefits of machine language in cybersecurity, caution should be observed for the following 2 reasons. Machine learning, just like humans, is inherently imperfect. There's a very good reason why the answer provided by the neural network is called a prediction. It's just that, a prediction. As you saw in today's example, while we can get incredibly accurate predictions from our network, it's impossible for 100% of the predictions to be correct. For this reason, we should remember that AI isn't the silver bullet for all problems. It will never be perfect, but it should be used in conjunction with humans to play to each of their strengths. The same power that allows machine learning to be used for defense means that it can also be used for offense. As we will show you in tomorrow's task, machine learning structures and AI can also be used to attack systems. We should, therefore, always consider this a potential threat to the system we create. So, if we go to the neural network, we're going to go to predictions, we're going to upload. And so we had 91% over 90% accuracy. So we got the flag. Neural networks are neat. So cool. Now, if you enjoyed this room, and we invite you to join our Discord server for ongoing support, exclusive tips, and a community of peers to enhance your Avid assignment. I'm already in the Discord server. If you're not in the Discord server, definitely join to meet other cool people. And yeah, it's great. So, we're done with this room. I hope that you learned something in this video. I know I did. As I said, I really haven't played with AI and machine learning, so these rooms are great to get a nice digestible size of learning different topics in cybersecurity. As you can see, cybersecurity is a very vast field. And so, again, if you want to continue learning, these Advent of Cyber rooms are good because it gives you other rooms to learn if you're interested in the topic. I feel like I'm rambling, so I will end it here. Again, I hope you learned something. I did as well, and I'll see you in the next one. Have a good day. Bye.